Okay, I'm gonna share screen then. Let's see. So probably seeing my screen. Let me find the right window here. Here we go. Okay, so for something completely different here for a few minutes introduction, this really does connect to our work. It's just that, as most of you know, the core of the Swift method is really image matching, as I think of it. So we have this part that is called by the code that Tom and all have been working with, called SWIM, which in my mind stands for Signal Whitening Image Matcher, part of the overall concept.
So are
So,
we supposed to be seeing Tom Bartol?
yes,
You are. Okay.
yes. So instead of nanometers, we're going to think in light years for a few minutes here
Okay.
to show the concept. Okay. So I know you've all been wondering where Tom is in the universe and the rest of us by implication. And uh, so a while back, actually in December, Tom sent me the full image that he uses for the background here. And I'm going to use this just to show the image matching component and a couple of things that relate to particular problems that we have, of course, with electron microscopy data that is not quite as pristine as uh, we would got as we got accustomed to sometimes. So the question then is, seeing Tom's background here, where is that? And of course, I always suspected, and was pretty confident in the fact that it was near the center of the galaxy. So this right image over here, you see this X-shaped thing is a good indicator, and the center of the galaxy is right down here somewhere. And Tom told me that the image was from M24, which is a clear area in the view here. All this dark stuff is dust, and M24 is over in here somewhere. It doesn't really matter
Uh,
for our purposes.
actually, actually, M24 is north of there, straight up. On the other side of the, I looked it up. It's on the other side of the central dust lane.
Well, we'll check that, but I think it's right
Okay,
here.
okay,
We'll double check that. It doesn't
okay.
matter for the purpose of what.
Yeah, yeah, yeah.
So either there are misnamings of all sorts of things here. So there's the Sagittarius star cloud. Sagittarius is a constellation, the teapot as we think of it, and you can't really even see it here. The stars appear so differently in uh, the night sky as we see it versus this. But again, we're getting off into the astronomy a little more than we need to here.
So are those red clouds H2
Yeah,
region?
those are nebula, Trifid's Nebula, and Tom help me
The
out.
one, yeah, the one you're pointing at there is called the Lagoon Nebula, and the one just above that is the Trifid Nebula. That one.
Yeah, and
Yeah.
you don't see those by naked eye, really.
No.
Although in principle, the resolution is such that we could, but it's just not going to happen.
Yeah, the Lagoon Nebula is bigger than the full moon.
Yeah,
Wow.
as you know, with the Andromeda Galaxy, it's very hard to see. It's
Yeah,
not in this view, but
and the Andromeda Galaxy is 6 times bigger than the full moon
yeah.
in the sky.
So anyway, given this view and given Tom's background, how do we put them together to find where it is? So let me show you the image where I first found the correspondence. And you could stare at this for quite some time and probably not see it. Once I show you, it will become evident probably. But anyway, the business about M24, I went off looking for images of M24 and trying to find a match. It was not succeeding. And then I sort of tried to think about what Tom must have been thinking when he was freewheeling, aiming his microscope, or his telescope rather. Then I thought he was looking for an area that was relatively free of these dust lanes and had a fairly uniform background of stars. And in our conversations, that's more or less right what he was trying to do. Tom, you can fill me in on anything there, but basically,
Yeah, I was just randomly, I looked at the Milky Way with my naked eye and I said, oh, that spot right there looks pretty bright. I wonder what it looks like in the telescope.
yeah.
And I just pointed the telescope by hand, I kind of sighting along the telescope, not really sure that I was even aiming exactly where I want, what I was seeing with my eye, but I took this picture. I pointed there and took this picture, and I was very happy with it. But
And
I
so
didn't know it. But
Tom is going out on a new Star Trek, and wants to recapture.
Yeah,
I think I found it.
You think?
There are two bright stars in kind of the middle, upper, just above the center, the bright one, and then there's another one to the a little bit below to the right, two bright ones, and I see two bright ones in Tom's star thing here.
Okay. I'm not quite sure I understand what you're saying, Terry, but in all likelihood, you're wrong.
Yeah, okay. Well, well, okay. Well, where is it then? Okay.
Okay, it's right down here. Right down here. Boom, boom, boom.
Oh my God.
And initially, I started looking at these three, but it's right here.
Well, there are different scales. How are we supposed to figure?
Yeah, exactly. Well,
Yeah.
that's the dilemma. We don't know the rotation. We don't know the scale. Okay, and finding those is really the key. And the way I found this was a combination of using my matching tools, but really by eye was the first thing, and this logic of we're looking for an open patch,
Yeah.
that does not have a lot of these dust lanes and so on.
Right.
And knowing how things go, probably the field of view here. This is Tom's full image, but reduced by 10. Okay. So you notice some vignetting on the sides, but the interior here is relatively smooth, but we do see some things here, right? So that actually was what tipped me off first, was notice the shape of that versus this.
So, Art, there's okay, if you look at Tom's, you see there's the brightest star, right? Which is the one I now can identify, has just below, there's like 3 stars in a row, or 4, I think.
Yeah.
And if you look carefully at Tom's thing, there's a lot of streaks of 3 or 4 stars.
Yeah. That's a dilemma. There's a lot of stuff that
I
looks
do
alike.
not think this is real. I think that this is a fake. Somebody, was putting together. Just look at, if you look at it carefully, there's just all these rows. In fact, row upon row upon row of stars. How that is not random.
Well, by whatever mechanism.
But the Big Bang would have sent out streaks, right? It would be in rows.
Yeah. No, I think that we're looking at dendrites. I think those are synapses. Dendrites, yes.
The universal dendrite here.
Is that right, Tom? That you got a picture of some neuropil and you?
Yeah. This could just, this is
to make it look like stars.
Yeah, I could just as well have taken, the images that Justin Kinney was making of the extracellular space with all the dots and everything that he generated,
right.
Taken something like that and just boom, done this.
Yeah.
Well, okay. Well, I believe you.
But wait till you see Art's swim proof, basically, of the match.
Okay.
Yeah, I was gonna look up that Sidney Harris cartoon. You want proof? I'll give you proof. But it's not. I jokingly say it's not quite proof. It's merely astronomical evidence.
Yeah.
Boy, I tell you, we have had a day of jokes today.
Yeah.
Okay.
So let's get to it and actually run some things here in the normal way that I do things here. So we have these couple of images. Boom, boom, boom. So let's start off with confirming the match between this this image and this image. And excuse me, I really should put these things into PowerPoints. It would save us all time. But so as we've seen in the last 6 months or so, we've had some image sets that are not quite ideal. Whereas the original set of tools that were developed that you've used more or less require really good quality images that have certain constraints, pre-constraints in terms of rotation and scale in particular that Terry, you mentioned, how do we know what scale to look for here? And there's a chicken and egg problem, certainly, to this. So what I just did was ran a log polar match that requires some fairly precise positioning ahead of time, and I'll show you here what I mean. So in this log polar match, in this case, you see we have this nice single spot. I'm always looking at these spots. And what this is the match of this against this. And what are these? Well, these are the log polar wrappings that go in sort of a circular arc around a particular point that we can think of as a center point for the matching process. And with this log polar mapping, the downside to it is that you really have to be pretty precisely aimed to begin with. But let me, come on here. I put my crosshairs there, and you see that that spot is slightly offset from the actual middle here. And that offset is communicated back to us and eventually to the user interface. So Tom will be interested in these numbers that we already use in the conventional image matching that give us XY offsets. But here the XY offsets are reinterpreted as scale and rotation. So in the complete affine solution, we need 6 numbers that give us effectively the scale in both directions and the shearing in both directions. And if the shearings are the same, it really is a rotation. And then, of course, we need the XY offsets. So that's the 6 numbers. So in this case, we get back 2 of those numbers, and I'll just plug them in here to a tiny little program I have that turns these numbers that are offsets in the image that I showed you that had the spot, returns those in terms of an angular measure, in this case 0.902, it doesn't matter what it is, a small sub-degree rotation, and a scale factor here. So using that information and maybe jumping ahead a little bit that I can discuss if needed, leads us to the next step, which is to go back then to a simple translation type of motion. So we use the polar and scale information to help us get the XY position, which I just did. And there's our spot again. Always like to look at that spot. And here is the alignment between these 2 images. Now, you see there's a little bit of residual there. And that residual is in large part because Tom was really zoomed in here. And of course, in the telescope, had a pretty flat field of view, did not suffer from barrel distortion like wide angle lenses do, or especially with zoom lenses, you'll sometimes get pincushion distortion. And this sky image that we're matching over here was somebody's shot, which I haven't been able to go back and find it, but this particular shot I would think is just a conventional camera synchronous polar rotation, so it could get a long time lapse. And so it suffers from a little bit of this distortion. That's what the residual is in this case. But again, the spot image is really the thing. And if we look at that spot, what that is doing is reproducing very closely the point spread function of the stars in the worst of these two images. Really, it would be sort of a product of the two distributions between Tom's shot, which is this one, and this other shot, which is here. And you notice the stars in this shot are not points, as they, of course, should be, but are a little bit diffuse. And so the correlation spot, or the match spot here, if we invert that to maybe make it a little clearer, is reproducing essentially the point spread function of the stars, the shape of the stars as we see them here. Okay? So, is everybody convinced that we found the proper match? Whoop, everybody still there?
Yeah.
Okay. I thought
I was
We all
waiting to hear
have to
from.
unmute to yell yes, Art. We're not in the same room.
Yeah.
I was waiting to hear what Terry thought of the match and whether he thinks this is random or made up and invented or is this real?
My question is, how did Art find the center point?
Yeah, that's what I want to know.
Oh, okay. Well,
To aim your log polar.
to aim that. Okay.
Yeah.
We'll take a minute and go back on that. Okay. So given that, then let me get the other images up here. I don't want that. Okay. Let's just start from here. Let's do it afresh, but in a strange sort of way. Okay. And see if we can do this. If we have the time to do the experiment, this could take a while. We'll see. So the program that I'm viewing this with is XV, which Tom I know uses, but I've hacked it a little bit so that when I click on something, it prints out the position. Okay, so I click there and I get a notation down here that says what image it is and where I clicked. Okay, and likewise over here. Okay, so I have those both conveniently in the same window there. All right, so I said that I first noticed this little wisp down here. Okay, and so let me click there. You can see sort of a swirl there, at least I can on the screen. And likewise over here. So what we are doing here basically is we're going to try some candidate spots. And to automate this, of course, for star fields especially, you would do some sort of procedure that is very analogous to what we all visually did here. We looked for the brighter stars and then sort of looked for matches. And so we would pair up presumably this star with this star and this star with this star. And most of them would be wrong. Okay.
That's what I did.
Yeah. I think that's what we all do. And so eventually we're going to find one that matches. Now, let's see what happens with the points that I just entered. That's what we got as our match. Okay. Now, there are two problems. One is the position could be wrong. The other is the scale could be drastically wrong, in which case we need to get within maybe 30% or so before this really starts to work. And if I look at my history for a second.
So Art, I think there's a simpler way of doing this, which is just
Okay.
do a cross correlation between the images.
Well, that's what we're doing as a cross correlation. That's how we get the spots.
No. But you do for the whole image, you just move it across, so that X and Y, and just compute the cross correlate. That's what you're doing. That shouldn't you get when it hits?
Well, the Fourier transform gives you that in one shot for a given rotation and scale.
Okay, that's right. You can't do that if it's you don't know the scale. You're right.
Yeah.
We're on to 6 numbers.
Right.
And the Fourier transform gives you directly 2 of them as output.
Right.
And that's the XY. And so that's what in the previous incarnation of what we were doing and Tom was taking advantage of was the fact that we were already close enough in scale and rotation so that matching process would work with high confidence. Here, of course, as we all see and was pointed out, we don't know what scale and we don't know whatever. So there is a certain search process in the sense of guessing, an intelligent search process to try to line things up. And, so here we have naturally the stars. In the electron microscopy, we might have other features, mitochondria or even cell nuclei, depending on the resolution and so on, that fit the same bill, and the same process as I use it here comes into play. So, where was I going?
Well, you have found this the dark spot that you thought was the place to look.
Yeah, exactly. So now what I know that it's fairly close in position between here and wherever it was down here, fairly close. But notice the scale is different. So that jumping the gun a bit here, if we look at the width here of these, whoops, wrong 3 stars, very easy to see the confusion there. These 3 stars are the match, okay? And even though the angle is a little bit different, we'll just fudge it here. The width of my selection here is 165. Now, again, putting the cart before the horse, knowing the answer to shorten our process here a little bit. Darn. The zoom thing is getting in my way there. Okay. So we see the same field in Tom's image here is 368 wide versus this other one is 165 wide. So excuse me again for a second. DC 368. Well, I don't even need to do that. Let me do this. Okay, so what I did was I used the ratios there of some known measure. I put that in. And now I get that. Okay. Now the spot is clearly evident there, but it has a white spot in the middle. And this is a artifact that sometimes shows up as a result of the way that this particular log polar is ignoring the middle of the disk, which I showed some time ago. And I have a fix for that, but it's not in this version yet. But at any rate, the numbers that come out here, then I convert those to a rotation and scale. And then we're going to go from log polar back to spatial domain XY positioning. So we're going to take exactly the same position that I just used there. And I know this doesn't mean anything to most of you when I'm typing here, but I'm using the same image position that I used for the log polar. And then I'm going to take the angle and the scale that the log polar told me. But the log polar, as I used it, was already scaled by this amount, 138 over whatever, so 0.448. Okay, so I'm going to multiply that. I do this all the time, so I apologize. It's not clear, I'm sure. And we'll get a crude match image here. Okay. And in this case, that did not center very well. Let me try to fix that. Oop.
I can't help but thinking this has got cancerous lesion.
I'm sorry, I didn't quite hear what you said there, Chair.
It's modeled. It looks cancerous.
Yeah, sometimes it is a pretty malignant process here. So what I was looking for here was a whitening that would give us a better match of the position. But let's just look at what we have here as far as the match as it stands. Okay, so we're in the ballpark, but we're not quite there. And we could fiddle around here for another 10 minutes and get it right on. But I don't know if that's quite worthwhile here for what we're talking about. I'll do it if you'd like, but
No, I think that's okay, Art.
Yeah, this is great. Okay, so we can actually see how you do this, for command line, which of course.
Yeah. And so Tom, calls these same programs unchanged and picks up the information that comes back in text form and then applies that to what you all see through the GUI, through the graphical interface. And so we could just as well do that on star fields as we do with your electron microscopy images. It's the same mathematical procedure underneath.
XV is as ancient as VI.
Yeah.
Just about.
And I use them both all the time. They are my mainstays. Okay. So let's see here what else I wanted to show with this. While I'm getting my thoughts back together, let me do one thing here. Yeah. For something totally different. And I just have a screenshot here to hint at it. I was going to get this ready to show today, and it's not quite, but I'll talk about it just for a second anyway. As you know, in lots of publications, there are, I lost it. There we go. There will be these images. In this case, it's a piece of cave art from 20,000 years ago or so that was recently discovered and had been missed in initial surveys of cave art. And you'll see over here on the left an actual photograph of this thing, which is not painted or whatever. And as you know, in the publications, very often people will put their drawings in over top of this. And I didn't screen capture what is really the convincing evidence, but you'll see here an example of the spot image that in this case is comparing just the black painted drawing versus the actual photograph of the artwork. And it's a pretty fragile, but you'll see the same spot thing in the middle, right?
Yeah.
So it actually managed to match the pen and ink part of the drawing, which I'm not showing here, with the actual photograph. Okay.
Cool.
So I'll bop out of that. So just to whet your appetite for all sorts of things that this matching process can do, that are very, very different, of course, from electron microscopy in terms of what they're really representing, but the same process works as far as the image matching. Okay, so back over here. One of the problems, of course, we have in the image matching is with, spurious information that does not contribute to the actual match. So if we look at this image, screen cap from last week, I think it was, as we were talking last week. Yes, I forget his name from Italy up here. So that's what this is. So
Franco Castelli.
Yes. So spurious information. Let's think about this image as it stands with relation to the way it matches with the image over here on the right. Tom is clearly spurious information, right? And so are the rest of us. Intruding on this scene and contributing to the Fourier transform that goes on.
Wait. Now I think that Tom is the figure here, and he is what we should focus on, not the background.
Oh, well, we're still focused on the stars despite Tom being forefront here. Wow. And it's
so I guess it depends on what images you're matching, right? So
yeah, exactly. Yeah.
So if you match that with a picture of me,
right,
then it would match, it would line me up, right? But if you match this to a picture of the stars, it'll match the stars.
Yes, exactly. Now, of course, the problem we have with matching you with other screen caps that we might have here is that you're always changing position, right? A little bit.
Yeah.
Well, we would be able to match you just fine, but we would not get these, 100-to-1 signal noise ratios or whatever. We would get 5s and 6s.
Yeah.
Something like that. Okay.
Yeah.
So let me cut to the chase here again. I see we're way, way along in time here. So let's do another log polar, and I hope I'm capturing the right thing here. Okay, so here's our log polar again, and again doing this cross centering, we see that we're off a little bit. But when I ran the program, it gave me back this information. And, we have a lot of extra information here that's useful to me for debugging and things, but it's really just these couple of numbers that are relevant to going forward in the process. So let's take that information and plug it back into the spatial domain. And I use a big, wide, almost full screen window in this case. And there's the spot for what I will show you next. Matching that with that. And we see we have a little residual. That is, in this case, I think mostly the effect of all the additional information here, which of course we could crop out or do lots of things with. But that's the result. And that's the evidence that it's correct. Okay. So again, not proof, but astronomically significant evidence. And what was the signal to noise ratio there? 38.7. So 10 to the 100th probability or something in that vicinity. Okay, I took way more time than I expected here. I thought this would be 5 minutes, but
okay.
I see it's 50 minutes.
So we better give Joel a chance to tell us about his progress. Since
so let me bail out of
go.
this. There's a lot more we could say about this, but we'll talk about that another time.
Thank you, Art.
Sure.
Just amazing what you guys are getting done here.
Okay, I'm sharing my screen. So thanks for bearing with me, everybody. Yeah, I just did something really dumb, which was to mess with permissions in my bin directory. Ultimately, I was able to solve it by reinstalling Anaconda and reconfiguring my environment. So I just wanted to present on some progress with regards to the SWiFT alignment app for aligning EM images. So, and by the way, I wanted to say thank you to everybody who responded to my request for feedback on the style sheet for the application. I put a few of them in here. I think this is the one that got the most votes. But this isn't functionality, and I'm really excited to show off some new functionality. So, I'm just going to do a little alignment project here and just use a small data set, and we'll just go through it. But the major new feature is the way the control flow works. So since the beginning of this project, I've wanted to make this so easy that my mom could do it, and that's sort of my standard. And I think with these new changes, I think it actually kind of gets us pretty close to that. So usually when you opened up the application, like when I opened it up for the first time when I first started working on this, like 4 months ago, you just have a control panel with all these controls, not immediately obvious, like how to do an alignment project in case somebody shows you. So,
Joel, are you telling me that
yeah.
you're using your mother as a beta tester?
She absolutely is. So, yeah.
A
So
few of us are even older than your mother, so we might be better testers.
oh yeah, but you're computer people. It's a different breed. So the features which are going to make this app super intuitive are the new UI flow, and the way the UI flow works is elements like widgets become activated and accessible only when they can actually be used. So instead of like having a ton of controls that, because there's key steps as you progress through an alignment project. First, got to import your data. You've got to select which images you want. You might have some bad images, and you've got to scale. So scaling and data selection, I consider that to be like one step, like the first step. So that's step one. Then step two is you align your images, and that comes with it. It has its own set of controls that have no bearing on the other steps. And then the final step is you have to export it to ZAR, and this is step three, the final step, export and view. So export to ZAR and then view in NeuroGlancer. And we've got our embedded NeuroGlancer that I've demonstrated in the past. Okay, so there's that. And I'm calling that like control flow. Like people who are in the business of naming things would call that UX flow, how like a user progresses through an application, and like what the experience is of actually using the application. So then another thing that helps is the warning dialogues. So let's try to like generate one of those right now. Oh, and an interesting thing. So since I came up with this new control flow, I found that it now makes it impossible to even get a lot of the warning dialogues that I spent a lot of time making. So I had all these warning dialogues for if you try to do something that's not supported or like that doesn't make sense, then the warnings will very clearly say like why you can't do that and what you have to do before you can use that feature. But a lot of those were like made like nullified because of the way I've got this now. So let me just show you. So I'll do a project from beginning to end. So when I go new project, it's gonna give me a new project save as window. So I'll just go into test projects. Just go. And then, so this is going to be our project file. And so you see that the scaling and data selection lights up here. And now we can use those controls. No need to overwhelm the user with like all of these other controls. So I'm going to import some images. We'll go to volume Joseph, the usual suspect. I'll just do 20 images. So, oh yeah, full disclosure, with these new changes, I did mess something up. I've got this bug here. You can see where I know where in the code I'm getting this bug, but full disclosure, but everything else should like work except for this. See how it's like following my mouse, so ignore that. Okay, so center, and then you know, you can go through the images, the reference image on the left, and then the current image in the middle, and then we'll get the aligned image stack right here. So then we click generate scales, we get a dialog. We'll just do just 2 scales. And now it's generating the scales. And now that the scales have been generated, it's a small data set, so it did it quickly. We get these controls. This is, there's a little alignment bug here. Ironically, an alignment bug here with this, but so this is like going to be your scale. I generated 2 scales so that if you could see here, it would say scale 1 and scale 4. So we're going to do an init affine and align this scale. Should be pretty fast.
And Joel, be sure to check the chat here. Kristen's giving you some feedback.
Oh yeah. Yeah, that's on the to-do list. That's on the top of the stack, Kristen. Great point. And that's why I dragged this over here so you can see what's happening.
That's the reason Reconstruct does that for us. I'm your mom.
Yeah, and it should be totally possible to do because the way you make a progress bar is it's well the usual way you do that with the progress bar is you have a loop in your code, and I think that Tom's task queue, which he wrote to schedule the blocks for both what's used in generating the scales and for the alignment, but that's perfect for a progress bar because it's a loop. It's looping over these many blocks.
I think there's a library that does progress bars, just does progress bars. It's called TQDM.
Yeah, TQDM. Yeah, I've got that installed.
Yeah,
I haven't messed around with it yet.
Should make it easy. I haven't tried it too, but
okay,
it needs to be advertised that way.
Yeah, definitely. All right, so here we are, and we've got our aligned images on the right, and we're all done. And oh, I didn't export it yet, so this is good thing I accidentally made that mistake. So this is an example of one of my error messages. So they all show these same 5 steps, and they say which ones haven't yet been completed. So thank you, warning dialog. I forgot to export the ZAR first. I forgot a step. It's easy to do, even if you've been working on this like all day. So export to ZAR. We'll just use the defaults here, but it's configurable to 3 different types of compression or no compression. C level is compression level. And I've started putting in tooltips. So like when you hover over C level, it will say C level is compression level. Haven't done that yet. But also you'll see these tooltips. Yeah, what's up, Tom?
Oh, I was just going to say another way to handle, cluing in the user what they should do next or what's valid and what's not valid is within one of your little boxes, you could have certain buttons grayed out until, for example, you could have the neural glancer button grayed out until you've exported the ZAR.
Yeah, good idea.
So then you get kind of a sub staging of processes within a given box.
So
yeah,
Tom,
that's perfect.
So Tom, I slightly disagree. I think it's better to, because when people see grayed out stuff, they think maybe it's not gonna work. If maybe instead you have a series of lights around the bars that tell you what order to do things in, like now's time to do this, the light comes up. And then if you try to if you try to go over to the neuroglancer bar, then up comes the nope, you can't do it yet. But I think if you have grayed out bars in any of this, it kind of cues the user that maybe the program isn't working right.
Okay.
Missing
Well-
some of the missing some of the bars that, you know, maybe they're just under construction or something.
Oh, I see.
You see what
Yeah,
I mean?
I guess, and that's the fault of other programmers.
Yes,
Who
but that's what we expect.
Yeah, they've used the gray bar in the wrong way. And we've all then come to expect that it really means, oh, it's broken or something.
Right. And that,
Yeah.
I think by, you know, having a sequence of colors, you know, because you can kind of see that you could light up the one that you should do next when it's time when you're done.
Yeah,
light
maybe
up, light it up.
Yeah, instead of gray something out, highlight the one that has to be done next.
Correct.
And if you don't do it, there could be errors. Yeah.
That's much better.
Yeah, that's
right.
a much.
And then if you don't do it, the click will say, "Oh wait, you got to go back and do that one that says."
Do that one. And remember, we lit it up for you. You should have seen it.
You can come to this one after you do that. There's a sequence here.
Exactly. I like that idea very much.
But you should also have the option of skipping it, right?
Well, only if it's valid. Only if it's valid to skip it.
Yeah,
Well,
so
we maybe just decide that, oh, I did it wrong. I'm going to start from the beginning, you know.
Oh yeah, you can always go backwards, but you just can't go forwards with data that's bad.
Yeah.
okay, so you can skip. So and you can skip at any point. So the skip functionality is early in the you always have access to the skip as soon as you import your data.
That's a different use of the word skip than we're talking about here. Yeah, we're not talking about skipping images. We're talking about skipping steps in the process.
Okay.
That's what we were talking about.
Yeah, sorry, I was thinking about what I was doing here, and I wasn't fully.
Yeah, no, the issue is that you know, I said don't use the gray out because people expect that means that that's still under construction or broken. But if you're going to use something that says do me next,
you could put a brighter box around it.
You put a bright box around the one that says do me next. But if you go forward too soon, up comes your error window that you showed us, which is really cool. If you go backwards, you get to go backwards because you're just going back through the series again, as Terry said.
Yeah, and if you go backward, that should then invalidate or change the highlight. Invalidate the step you're at and highlight something, you know, that's, you know, change the highlighting to be the appropriate next thing again.
Right.
Yeah. I like this a lot.
This is exactly the kind of thing that, I mean, a lot of the steps in Reconstruct do that because I was such an idiot. I was John's idiot user, right? I would make these mistakes and I'm like, why isn't this working? He said, well, it is working. It's just, you know, you're being impatient. So then you have the abort button, or you have the I'm working, can't abort right now button, or whatever coming up to let me know where you are.
And maybe some of you have heard the cliche about making things idiot proof, right? So there's a saying that says, you know, as soon as you think you've got something that you've made idiot proof, they make a better idiot. They make a better idiot. Yeah.
I was the best possible idiot and still am. That's why I'm your mom.
No, actually, to be an original idiot takes talent.
That's right. I don't profess to have no talent, Terry.
No, I'm talking about Tom's comment about inventing it.
Exactly.
Yeah.
Educating idiots.
Educated idiot. Mm-hmm.
Yeah. And this is what makes software testing, unit testing, and validation so hard, right? These are unsolved problems.
The flip side of that, though, is to make it so that it's not unfriendly to the experienced user at the same time.
Right.
That's the challenge too, right? So that people who know what they're doing can zip along without being forced to do each step.
So the way that's done, notice in a lot of programs is that there are function keys that allow you to skip a lot of steps, you know, on the keyboard. And so that,
Yeah.
that way, you know, for things that you do repetitively or often, it's just a minimal amount of effort.
Yeah. And that's what we're trying to achieve here through this tool.
So
I
here in,
really am, I'm really impressed with this new GUI. It's really, really spectacular. And also it's going to be really nice because once you start to implement virtual sections and total alignment, you know, you're going to be using the same tool,
Yeah.
right? And
Yes,
so you might want to keep the same number of boxes here, but you may also just want to make your alignment box a little smaller, or within the alignment box, you may need to add, you know, a virtual tool, or within the expert in view. I mean, somewhere you're going to need to add the buttons for virtual alignment from TomoSem, and that might be on the second page or something.
Yeah. Or a different mode of operation of the GUI, right? So if you go into that mode, then the boxes along the bottom of the screen change to
Change, that's right. And maybe what you
Yeah.
have at the top under file, you know, or someplace along the top, you have, you know, serial section alignment, virtual section generation from TomoSem or from IMOD or whatever. So
Yeah.
you have the drop down menus at the top that would call up the bottom boxes.
Right.
yeah, these are all great ideas.
I think
Here-
I like
here
the
I've-
gray background at the bottom better than the black with white on it. For
So-
you're
I
showing
agree
something
with
different
that.
here.
Yeah, I agree with that. It's too contrasting. And actually, I find that by reading white letters on a black text, when I look elsewhere, it really looks screwy. It's the retina adapts to it in a way that
That's right. And then it's hard. It's good to see color in a black background in a dark room, but I think your gray was better.
Yeah. So just a few things. What I'm showing on screen right here, these are very large images. These are like as large as it gets ones. They're like half a gigabyte per image. And I'm aligning a few of those just so that it handles large images. You know, I really think like the way this all looks really is cool when it's not doing this it's following my mouse. This is something really silly that I'll probably figure out as soon as we get off this call.
Mhm.
So I wish it wasn't doing this
Yeah.
because it makes it look kind of, but
you could click it. Can't you click it?
yeah, I am clicking it and I tried plugging in a mouse, but I know which part of the code I was working on, and it makes sense that I could get a bug that presents like this.